Next slide. With this introduction of stars using the sun as our model, let's look at stars in general. Stars are entirely gaseous. Three things describe gases: the temperature, pressure, force per area, and the density, the mass per volume, and the relationship between them is the equation of state. This animation shows that cool gas produces low pressure, while hot gas produces high pressure. Stars are round because gravity holds them together. The outward thermal and radiation pressure is balanced by the inward gravity compression. This balance is called hydrostatic equilibrium. If there's greater gravity compression inward, there must be more outward pressure to balance it, and the gas creates that extra pressure by heating up. Decades before astronomers knew about nuclear fusion, they had a good model of how the density and temperature of stars increase towards their cores using the idea of hydrostatic equilibrium. Deeper layers have more gravity compression from the overlying layers. The greater gravity compression raises the density of the gas. In order to balance the greater gravity compression, the outward pressure of the gas and radiation is increased by raising the temperature. Calculating the change in density and temperature layer by layer toward the center of a star, you find the temperature at the core of a young star is equal to 8 to 28 million Kelvin, and the densities equal 10 to 130 times the density of water. As stars age, these numbers increase. Next slide. This slide is about nuclear fusion in stars, which occurs only in their cores. Stellar cores are above 8 million Kelvin, and the density of the gas is much higher than the densest metals on Earth. Even though the gas density is greater than any solid material we have on Earth, the temperature is so extremely high that the core is still a gas. The sun has a tremendous luminosity of 4 times 10 to the 26 watts, which means in 1 second the sun generates the same amount of energy as 2.5 billion of our largest power plants generate in 1 year. Now there are several ways to generate that amount of energy, but they can't keep it up for as long as the sun has been shining, that is for 4.6 billion years. Only nuclear power can. The most efficient chemical reaction could power the sun for at most 30 years, and from personal experience I know that the sun has been shining for longer than that. Continual contraction of the sun could keep the sun hot for about 30 million years, but the geological record shows that the sun has been shining for much longer than that. So it's a problem of time scale, not the luminosity. Nuclear power is the only thing left to power the sun for as long as it has been shining. There are two types possible: fusion and fission. They both transform the nucleus of an atom into another type of nucleus. Fission produces energy by breaking up massive nuclei like uranium into less massive nuclei like helium and lead. Fusion produces energy by fusing together light nuclei like hydrogen to make more massive nuclei like helium. Atomic power plants and the atom bomb use fission to get the energy. Stars and hydrogen bombs use fusion. To get the positively charged nuclei to fuse together, their electrical repulsion must be overcome. Remember that like charges repel and opposite charges attract. Once the positively charged nuclei are close enough together, another fundamental force of nature called the strong nuclear force takes over. It is much more powerful than the electric force and makes the nuclei stick together. To get those nuclei close enough together requires high temperatures and high densities. At high temperatures, the nuclei move fast enough to be driven close enough together for them to fuse. The high densities ensure that there are enough nuclei within a small volume for the collisions to take place at all. The only place these extreme conditions occur naturally is in the cores of stars. Hydrogen requires temperatures above 8 million Kelvin to fuse, and helium requires 100 million Kelvin, and elements with more positive charge require even higher temperatures and densities. In the nuclear fusion process, in normal main sequence stars, 4 hydrogen nuclei, protons, are fused together to make one helium-4 nucleus plus energy. The helium nucleus has slightly less mass than the 4 protons that created it because some mass is converted into energy by an amount given in Einstein's famous equation E equals mc squared. Next slide. Nuclear fusion uses a chain process to build up the helium nucleus. This animation shows the simplest chain process that involves 3 steps. Another chain process found in stars more massive than the Sun uses a 6-step process. The net result of the chain process is that 4 protons are fused together to make a helium-4 nucleus, plus a gamma ray, plus a positron, the antimatter counterpart of an electron, plus a neutrino that we'll talk more about in a bit. Why do stars use a complicated chain process? Wouldn't it be much simpler if 4 protons would collide simultaneously to make one helium nucleus? Simpler, but not very likely is the answer. Getting 4 objects to collide simultaneously, each with high enough energy, is very hard to do. The chances of this happening are very, very small. The collision of 2 particles together at a time with enough energy to fuse are much more likely to occur than the simultaneous collision of 4 particles, each with enough energy to fuse. So nature slowly builds up the helium nucleus. Next slide. Notice in the first step of the chain process that a positron and a neutrino are created. A neutrino is a subatomic particle with a very small mass produced in nuclear reactions that rarely interacts with ordinary matter. Neutrinos travel at nearly the speed of light and provide current information about the number of nuclear fusion reactions occurring in a star's core. Photons are made from a variety of things. Neutrinos are made from nuclear reactions. If nuclear fusion is going on in the Sun, neutrinos would be produced. If we had a way of detecting these ghost particles, they would give us very recent information, just 8.5 minutes old, about the number of nuclear fusion reactions in the Sun's core. Because the number of reactions is very sensitive to conditions in the core, solar neutrinos would tell us about conditions in the Sun's core as of 8.5 minutes ago. Photons take up to about 1 million years to leak out. The light we see now from the Sun was produced a long time ago. How do you detect something that passes through ordinary matter easily? Because neutrinos very rarely hit ordinary particles, you need to increase the chances of even a few neutrino interactions by using large amounts of special materials that react with neutrinos in certain ways. A chlorine isotope will change to a radioactive isotope of argon when a neutrino interacts with it. In the same way, a gallium isotope will change to a radioactive isotope of germanium. Water molecules will give off a flash of light when struck by a neutrino. Neutrino detectors are buried deep underground to shield them from cosmic rays which would contaminate the detection. Even the largest detectors detect only several hundred neutrinos in a year. In the first 3 decades of neutrino observations, they turned up a mysterious lower number of neutrinos. Just 1/3 to 1/2 of the expected number of neutrinos were detected. The puzzling lack of neutrinos from the Sun was called the Solar Neutrino problem. The Sudbury Neutrino Observatory was built in Canada to find out what's going on with the neutrinos. It firmly established that some of the neutrinos produced by the nuclear fusion in the Sun do change into other neutrino types which couldn't be seen with the earlier detectors, and that the solar nuclear fusion models do predict the correct number of neutrinos. The ripple effects of this discovery spread out into our understanding for the evolution of the universe, which we'll get into in the last week of the semester, and also into our fundamental understanding of the structure of matter. Next slide. Our computer models of star structure using hydrostatic equilibrium, gas physics, and nuclear fusion enable us to understand other things about stars, such as the ones shown on this page. Observations of thousands of main sequence stars show that there is a definite relationship between their mass and their luminosity. The more massive main sequence stars are hotter and more luminous than the low-mass main sequence stars. Furthermore, the luminosity depends on the mass raised to a power p, that is between 3 and 4. Massive stars have larger proportion of radiation pressure than gas pressure, so the power p is closer to 3, while the low-mass stars like the Sun have power p equals 4. Either way, it means that even a slight difference in the mass among stars produces a large difference in their luminosities. For example, an O-type star can only be 20 times more massive than the Sun, but have a luminosity of about 10,000 times as much as the Sun. Massive stars have greater gravitational compression in their cores because of the larger weight of the overlying layers than that found in low-mass stars. The massive stars need greater thermal and radiation pressure pushing outward to balance the greater gravitational compression. The greater thermal pressure is provided by the higher temperatures in the massive star's core than those found in low-mass stars. Massive stars need higher core temperatures to be stable. The nuclear reaction rate is very sensitive to temperature, so that even a slight increase in temperature makes the nuclear reactions occur at a much higher rate. This means that a star's luminosity increases a lot if the temperature is higher. This also means that a slight increase in the mass of the star produces a large increase in the star's luminosity. The star structure models also explain why there is a star mass cutoff at the low end, with the smallest star being just 8% the mass of the Sun. That's 80 Jupiter masses. Gas balls smaller than that cannot achieve the temperature in their cores required for nuclear fusion. These failed stars are called brown dwarfs. They're too massive to be considered planets. The picture shows the first brown dwarf discovered on the left, and the Hubble Space Telescope view of the object on the right. On the high mass end, the star structure models explain why there is an upper limit on star masses, with the largest masses now observed to be about 100 or so solar masses. Stars with too much mass have so much radiation pressure inside pushing outward on the upper layers that the star is unstable. It blows off the excess mass.